hello. Hi, everyone. Welcome to day 2 of week 3. We're going to go ahead and tackle 2 more sections of our unit 4. Let's get started. First thing I want to say is that I have this wrong right here. I put 1 previously, it was pi over 2, so just make sure you update that on your notes. Um, then we can just start here. Okay. So 4.3 is called divergence and integral test. So, when given a series, there are 2 underlying questions. Is the sum going to add up to a real number, which means that the sum converges, or not, which means it diverges? If the series converges, what is the sum? The first question is important. If the series diverges, there is no point in trying to determine the sum. We will see that there isn't one particular method for determining whether a series converges or diverges, but rather a collection of methods called tests. The divergence test, the integral test, the limit comparison test, the alternating series test, the absolute convergence test, and the ratio test. Let's go ahead and look at the harmonic series as an example of the summation being convergent or divergent or not. Now recall that this setup can be approximated with this integral. And in doing this integral, we don't really do integrals with infinity. We express them as a limit. So let's see if we can approximate this integral, or get this integral, really. Well, we know that the integral of this is just, hold on, I accidentally chose to rewrite it, is equal to, oh wait, t is equal to ln of x with t and 1, with the limit as t goes to infinity. Then for here, we just plug those in for the limit as t goes to infinity of ln of t minus ln of 1, which is just 0. So we're just being asked the limit as t goes to infinity of ln of t, which we know here that is infinity. So it does not add up to a real number, so this diverges. And if you see a pattern like this with the harmonic series, or if you see a notation like this, where it's the sum of fractions, that is a divergent series. Now, let's go over one of the tests, the divergence test. If the sum of a series converges, the terms of the series have to approach 0. Now suppose the sum of the series is a series in which we do not know whether it converges or not. If the terms of the series do not converge to 0, then the series cannot be a convergent series. Therefore, we have our first divergence test. So, the divergence test reads as follows. This reads, if the sum of the series, or if the sum is a series in which the limit of what's inside the series as n goes to infinity does not equal 0, then the series diverges. Now, this is not necessarily an if and else. It's just an if. This test does not tell us what happens when the terms do converge to 0. If the limit as n goes to infinity of a series goes to 0, the series may converge or diverge. We just saw the harmonic series. Now the harmonic series, we proved that it diverges, or its sum diverges. But if we should just tackle this limit alone, we know that that does equal 0. But for the geometric series, you could argue, well, it's written like this sum converges. But the limit also does equal 0. So this test is not, it equals 0, now what? It's literally you checking if it doesn't equal 0. If it doesn't equal 0, then you're allowed to assume it diverges. You're not allowed to assume the opposite. Because it equals 0, it converges. It just doesn't equal 0, diverges. Plain, straightforward. Okay, when the terms of a series approach 0, the divergence test is inclusive, and another method must be used to determine if the series converges or diverges. So, example 1 reads, what, if anything, does the divergence test tell us about each of the following series? So we have this guy first. And what we're going to do is we're going to take the inside of the sum, and we're going to make it to where it's the limit of n going towards infinity. So for here, we're going to use one of our limit properties where we can just write the limit inside this function, the limit as n goes to infinity of 1 over n squared. And we know that this is a bottom heavy function, so that will go towards 0. So sine of 0, which we know sine of 0 is, well, 0. So here we show that the limit equals 0. So that means the divergence test is inclusive. And it didn't really tell us anything, unfortunately. And we would have to do another means to figure out if this sum converges or diverges. Let's go ahead and tackle here. Now, this, technically, is a polynomial on top and a polynomial on the bottom. That really, what we can do with this is we can evaluate this using Hospitals, because both the top and the bottom will go towards infinity. So Hospital because of infinity over infinity. For the first one, it's going to be 6n. And for this one's going to be tricky. You do 1/2 1 over the square root of 4n 4 plus n, and then you multiply it by the derivative that's inside, which is 8. No, not 8. 4 times 4, so 16n to the power of 3 plus 1. Okay, so we have to mess with this a lot a bit. Let's go ahead and let's leave that on the bottom. We have 16n3 plus 1 over, and then we put the fractions on top, so 12n, combine the 2 and the 6, and then square root of 4n to the power of 4 plus n. If you do this, I actually don't like doing Hospitals here. I think Hospitals here is kind of a moot point. What we could do with this instead is mess with the factorization of n, and then just move the limit inside of that square root and on top of that fraction. I think that's what we're going to do. So let's go ahead and see what is the largest thing we can factor here and here, and see what they match. Here, I'll go ahead and leave this as incomplete work, because the Hospital method didn't work. Let's go ahead and jump to us just doing it as 3, wait, let me write 3n squared minus 1, limit as n goes to infinity square root of 4 n4 plus n. The max n you could take out of here is n squared. That's what I'm going to do. N squared times 3 minus 1, with the minus all ugly, n squared. And then, where's my whiteout? Oh, there it is. And then, the top here, you can factor out n to the power of 4 from the inside, and it'll escape as n squared. But really, you'll have 4 n's by itself, and then plus n over n to the power of 4, which actually we can just simplify that to be 1 over n to the power of 3. You cancel those n squares out, and you're left with the limit as n goes to infinity of 3 minus, or I guess you don't need the parentheses anymore. 3 minus 1 over n squared over the square root of 4 plus 1 over n to the power of 3. Then from there, you can move your limits piecewise, and you can go inside the square root, and you can see that the top would just be 3 minus 0, and the bottom would just be the square root of 4 plus 0. That's going to be 3 over 2. Now, at the end of the day, what this tells us specifically is that because the limit of this, not the sum, the limit of this does not equal 0, then it's safe to say that this series diverges. Diverges via the divergence test. Okay, let me go ahead and just quickly look at how my answer key had it, just in case I didn't miss anything. Okay. Right. Okay. So again, the divergence test, because this is the last one, divergence test. You're checking if the limit of what's in the sum, not the sum, of what's in the sum, if the limit does not equal 0. If it doesn't equal 0, then it diverges via divergence test. If it does equal 0, then you need to do something else. We're going to learn some of these something else. Let's talk about the integral test. Suppose we call a step in the series a function of n, which technically, I know like in pre-cal I talked about this notation, so maybe you've seen this notation before, but it's interchangeable in this way, where f of x is a function that is continuous, positive, and decreasing for all x's greater than or equal to 1. Then either both converge or diverge. So both of these things have to converge or diverge. So when I express this guy here, remember, the gimmick with this is that we don't say infinity. We say the limit as some t goes to infinity of the integral 2 to t. 1 over x times ln of x, all of which is squared, dx. This is supposed to become something, a real number, not just, infinity or it doesn't exist or some kind of thing like that. Okay, for here, this is a u substitution because I see that the derivative of ln is right there. So 1 over x dx. So in using that, I get 1 over u squared du. And then we know that the derivative of that is, the integral of that is, I'm going to do it out loud. We have u, -2 plus 1, so -1 over -1 from t to 2. I'm going to go ahead and factor out the negative. And I'm going to plug in back u. One over ln of x. Okay. T2. So let's do the t and the 2. I'm going to go ahead and just do an arrow this way. We have negative, and then the limit as t goes to infinity of 1 over ln of t minus 1 over ln of 2. Well, if t goes to infinity, this bottom term is going to go to infinity. So that means this will just disappear into a 0. This, however, doesn't have t in it. So really, evaluating the limit gets you 0 minus 1 over ln of 2, which after simplification is 1 over ln of 2. Now, this says that the integral converges. And then by the integral test, the series also converges. So the answer is that the series converges. But the way we figured it out was we did the integral of that first. Now, keep in mind there is something I purposefully glossed over. I glossed over the fact that this function has to be continuous, positive, and decreasing. And I didn't really talk about this function being continuous, positive, and decreasing. Oh, for all x's greater than or equal to 1. But you see here, and it's drawn graph, that if you do just a little dotted line at the x is equal to 1, you see that it is making this decline. And it is continuous, there's no gaps, and that it's positive. So, the only thing, or it's not positive at exactly 1, but it's definitely for where it exists, it is continuous. So just keep that in mind, right? Because it's for all x greater than or equal to 1, but within its domain. So this one is a little bit tricky in that way. But the point I wanted to make is that let's check for all of these if even the integral test can be used. First, we have the function cosine squared of n, and we see that written here. Well, first we want to check if it's continuous, and it definitely is continuous. Is it positive? It's definitely positive, but is it decreasing? At moments, but it's not continuously decreasing, so no. We see that it goes down, but then it comes back up. So therefore, that disqualifies it. What about over here, this function? Well, this function is continuous, except for when the bottom part is 0, but we really only care if it's continuous for the x equal to 1 part. So we could even write this line here. And if this line here is it continuous? Well, definitely. Is it positive? Well, it gets super close to 0, but it doesn't seem to pass the x-axis, so it seems positive. Is it decreasing? Actually, yes, it is decreasing. It keeps going down. How about over here? So over here's a bit finicky, but this guy will break several rules. Is continuous? Well, yeah. Is it positive? No. There are 1, 2 bouts where it's negative. And is it decreasing again? There's moments where it's decreasing, but it's not continuously, or it's not consistently decreasing. So just keep those in mind for continuous, positive, and decreasing. Right. Next, a p-series. A p-series is of the form 1 over n to the power of p, where every tick in the series is just you raising that tick to that power p. We see that p when is equal to 1, it looks just like fractions. When p is equal to 2, it looks like the squares fractions. P is equal to 1/2, it's the square roots. When p is greater than 0, the function is continuous, positive, and decreasing. So by the integral test, either both converge or diverge, both being the both being the sum and integral. Suppose p is a positive number other than 1. Then, as we do the integral, we would go ahead, or let me do step by step. So you would have the integral here. You place the improper integral with its limit. Then you go ahead and perform the antiderivative. You would simplify as much as you can. And then you would go ahead and plug in for this antiderivative t and 1. Here, you could eliminate all of this to just be the constants. Oh, well, I guess for here, you also have to acknowledge that when 1 goes to the power of anything, it's still just going to be 1. And then for here, really, you are forced to not really evaluate this any further. Because while you can evaluate this limit, we left p to be arbitrary. It's just a positive number that is not 1. The value of the limit right here depends on where the exponent 1 minus p is positive or negative. We know that when we have a variable x and it has a positive power, then it will go towards infinity. However, if it has negative power, it's written as 1 over that positive version of that power, and therefore that becomes bottom heavy, and that goes to 0. So, looking at this limit, P1 is positive when 1 minus P is greater than 0. In that case, when it's greater than 0, then this limit, or I'm sorry, this limit over here, when it's greater than 0, will just go towards infinity. So infinity minus some constant, because P would be defined here, is still unfortunately going to be infinity via the integral test, because the integral is divergent. Oh wait, I made a mistake. It's not going to be equal to infinity. It's going to be divergent. See, even I was messing up the difference between it being divergent or not. So we have to be careful with the language. Divergent. Okay. Here we see that it's going to be negative when 1 minus p is less than 0. Therefore, this series gets to be called convergent. Because we'll see here, or actually, let me write it here. This is just going to be infinity, and this is going to be 0. So therefore, it's convergent via the integral test, because the integral is convergent. again, just a technicality of this test as well. We have the luxury of these inequalities. But really, what these inequalities can tell us is the actual value of p. So we just add p to both sides, and you technically get 1 is greater than p. And here you get 1 is less than p. So that means that as long as p is positive, right? Because that's the sort of caveat of this setup. P is a positive number. If that p is a like a fraction, a decimal, something that is less than 1, then technically, as we do this limit or this p series over here, those values are going to get infinitely increasing. Whereas here, when p is greater than 1, then the bottom value is going to increase. And as the bottom value increases, it makes the whole thing bottom heavy. And eventually, if you divide it by bigger and bigger and bigger and bigger number, then you will get something super, super small and eventually 0. Now, oh, so at the end of the day, you could also take the claim that a p series converges, diverges when p is 1 is greater than p, or when p is less than 1. So just keep that in mind. Uh, there is an issue that occurs when it's negative, but for that, that's going to be the absolute test. But we're going to worry about that test in tomorrow, because we're going to finish this section by tomorrow. By the way, also, make sure you look at the schedule. I made a slight schedule change. I was re-looking at the Unit 5 lectures, and I kind of realized that that'd be a little bit crazy to finish all of Unit 5 on Thursday. So I went ahead and halved it. So Monday of next week, we'll have the second half of Unit 5. And that also does imply that, like, your test will only be Unit 4 and then that first half of Unit 5. And your test 4 will have the second half of Unit 5 and Unit 6. Okay. Is that it? Yes, that's it. All right. Next, and I think it's just, yeah, this is like the last page kind of. The limit comparison test. Suppose the sum of this series and the sum of this series are two series of positive terms, and the quotient of the series equals sum L, where L is a non-zero number. Then the sum of the sum of these series respectively either both converge or both diverge. So think of the sum of this series as a series you wish to analyze, and the sum of this series is a simpler series that we already know whether it converges. Use the limit comparison test to determine whether each series converges or diverges. So we're going to start here. Now, for this guy, what is a bit tricky is the usage of these polynomial expressions. So what I'm going to do is I'm going to go ahead and compare this to something that just has the coefficients, the singular polynomial expressions. So the sum of, let's say, just the leading coefficients. In my example, I don't have. You know what? For fun, I'm gonna go ahead and do that. I'm gonna go ahead and do if we didn't have them. So 3n squared, 6n 3, which you can technically simplify that to be 1 over n. But I'm gonna be risky and go a little bit off script and see if this will work just as well. Now, for context, this series, right? Because we can relabel this as a harmonic series because the n's will cancel out, it'll be 1 over n. We know this guy, this diverges. So if the quotient of these two series diverges, then by the limit comparison test, this guy is also supposed to diverge. So let's go ahead and actually set this up. So we have an to be the more full expression, and bn to be the simpler version, and we're going to go ahead and divide them. So we have an over bn is written as, I'm going to change it just a little bit, an times 1 over bn. So that way I can just write it as one whole thing. 3n squared plus 2 over 6n to the power of 3 plus 5n times, switching these, 6n3 over 3n squared. So I'm going to go ahead and multiply those guys. I have 18 and 5 plus 12 and 3 over, what is that, 18? Yeah, 18 and 5 plus 15 and 3. Just double check. Yes. Okay. So for here, you can see. Hold on, I want to make sure. Did I do it right? Yes. So from here, it's asking if this series converges, which we technically already know it does. As if we're doing the limit. Wait, let me just double check. Yes, okay. The limit of this guy, as n goes to infinity, of this grand sum, 18 and 5 plus 12, and not grand sum, grand expression. Grand sum implies a sum. That's why it's not true. Then for here, you would say, well, it's a balanced equation. So you know that this limit does equal, well, you know this limit equals 1, or 18 over 18. However, because of this technicality, now we have to bring up the divergence test. So because the limit does not equal 0, then via the divergence test, the limit diverges, and via the limit comparison test, our sum also diverges. Okay. Let me just make sure that I brought up everything. Because let me look at the limits, the divergence test. That diverges because it's basically harmonic series. Um, and we know that for the limit comparison test, alright, let me go ahead and I want to make sure my language on this is right. Because something that I wonder if it's a flaw in our notes, but something that I'm curious about is that when we're doing the limit comparison test, we're comparing the quotient of the sum. So I just want to make sure that for the limit comparison test, the quotient includes or does not include the sum. Give me a moment, let me just quickly check. So it's just as equal to 1. I think I messed up because because hmm, let me reread that again just in case. Oh, I confused it. That's right. We just have to check if L is a non-zero number. If L is a non-zero number, then they both converge or diverge. I don't know why I brought up the divergence test because when I said that, I was like, wait, we're not even doing a sum. So really, then so I could just take this. Actually, I should just write it out because in reality, it's just then via the limit comparison test because our limit is non-zero. Then our sum also diverges like the comparison. Okay. Yeah, sorry. I think I confused the strategy on top of the other strategy. That's on it. Okay. All right. This problem. So this problem, it looks a bit ugly because we have two terms here that are going towards n, and really we prefer if they were on top, just so we can split them up and maybe treat it like as two different geometric series potentially. So it's plausible to just treat it that way if it was on top, but because it's on the bottom, we have an issue. So we might as well just pretend that we have one of them. So you can pick either 7 or 2, or maybe just, do some kind of meshing and compare that. Compare this to say just the limit, I mean this infinite series, infinite sum of 1 over, I did 7 over 7 to the power of n, so I'm going to do 2 to the power of n in this example. Okay, now 2 to the power of n, that's just a geometric series because you can rewrite it as this, and we know that's geometric, and because would be the r is less than 1, then that means that this sum converges. So now the goal is that if this L, or if this quotient is an L that is non-zero, then this guy also has to converge. But let's go ahead and construct that L. We're going to let AN be 3 over 7n plus 2n. We're going to let BN be um 1 over 2n. In that case, we write the quotient like here, but then I'm going to go ahead and split it up just so it's a bit easier to do. So we have 3 over 7n plus 2n. And then we have times 2n. So I'm going to go ahead and I think I want to factor 2n out of the bottom. So that way, if I factor 2n out of the bottom, I can go ahead and cancel out the 2n here. So it's going to be 7n over 2n plus 1. So they're going to cancel out. And you're left with 3 over 7 over 2 power of n plus 1 of, well, all of this is, I forget to write the limit the whole time. Limit n goes to infinity. I'm going to rewrite it here just so hopefully you're following along. N goes to infinity. From here, I'm going to go ahead and take away the 3 to be on the outside. So 3 times the limit as n goes to infinity. And then, issue. The issue I have here with doing it with this is that this fraction is not gonna, this guy doesn't converge, or it doesn't become a specific answer, because we have 1 over 7 over 2n plus 1. And this guy is a positive number that's greater than 1. So, we're gonna get the limit of this technically goes towards infinity. And I'm gonna spoil it for you right now, that's not the answer. So I'm trying to see what else is there to do. Because the 3 escapes, that's fine. Did I divide by this right? I did. 2. 2 and 2 and just out. So 2. The limit of the bottom. Because technically, this becomes a bottom heavy function, right? So this guy, because we know the limit of this term is infinity, then it's just going to be 3 times 0, which means it equals 0, which means this guy doesn't converge, but it's supposed to. I think I'm gonna end the video here, and then you'll probably see a part 2 on what maybe my mistake was for this last question. And then you can go ahead and just correct it from there. So by the time you see this, I've figured out the explanation, but I need to in real time figure this out. So I will literally see you all in a bit.